For this problem, we're not going to make explicit use of any of these four methods given in this section. Problem is, suppose x and y are real numbers. Prove that if x squared y equals 2x plus y, then if y is not equal to 0, then x is not equal to 0. Okay, so it's sort of a compound if-then statement. We have our goal, our given, and here's how we can write our goal in logical notation. Right? If this equation is true, then this if-then statement follows. All right? So the parentheses are important there. Well, we need to sort of decompose this statement here a little bit. And the first thing we can do is just direct proof. Just bring the p over as a given and leave the q as a goal. So that's a good start. And then we still have an if-then statement as our goal. And we have to choose between direct proof and proving the contrapositive. I'm going to prove the contrapositive because I want to get rid of these not equals, which are a little bit hard to work with. Right? It'd be better if they're equal signs. So we want to bring over the negation of x not equal to 0 as a given and the negation of y not equal to 0 as a goal. Now, if you really wanted to somehow do a proof by contradiction here, then you could do direct proof, which would leave you with x not equal to 0 as your goal, and then you could do proof by contradiction to get that. But it's a little bit simpler here to just prove the contrapositive. So bring down our other givens, and the natural thing to do here would be just to combine these two equations, right? To substitute 0 for x up in the first equation. And when you do that, the first two terms go away and you're just left with y equals 0, which is what we want. So that's all there is to it. Now we have to figure out how to write this up, explain what we've done. Okay. So first thing we did was just direct proof, right? So let's say what we're supposing. X squared y is equal to 2x plus y. And then the next thing we did was to try to prove the contrapositive, right? So we should say we're going to do that. And instead of just saying we prove the contrapositive, because there's sort of multiple statements involved here, we should say what we're going to prove by proving the contrapositive. So we're going to prove that this statement here, right? That if, and make sure to put it in English, not logical notation, but if y is not equal to 0, then x is not equal to 0 by proving the contrapositive. Okay. And for that, we suppose that x is equal to 0. And all right, then we just combine the equations by substituting. So substituting 0 for x in our equation up here. We get, well, 0 on the left side and y on the right side. And well, that's what we needed, right? We're proving the contrapositive. So if you view that as y equals 0, then we're done. But let's sort of unwind the layers here just to be extra clear. Right? So therefore, we've completed our proof of the contrapositive. So we know that if y is not equal to 0, then x is not equal to 0. And so that finishes that layer. And now we're all the way back out to our original layer, which was a proof of this entire statement, right? And so we should say that. Therefore, if that equation is true, then if y is not equal to 0, then x is not equal to 0. Okay? And now we're done.